Okay, so this is the third part, and I left everything for the third part. And if I don't answer your questions, you have the fourth part, which is the break. Okay. So I want to talk about some keywords. Okay. I'm going to talk about proactive versus reactive. Reactive is you after the fact. Proactive is you predict and you react before it happens. Streaming data collection. Big data and cloud computing. Predictive data analytics, so you're going to do some prediction all the time. And some joint optimization of controls and driver decision, and actually joint up scheduling of controls and driver decisions are routing of drivers. And this is something which traffic engineers have not done. I'm really going to manage at the lane level and not at the road level. Because if you look at traffic, if you speak to traffic engineers or simulators and all, they take a bunch of lanes and they put them in one single link. So their network algorithms are simple, link by link. My network algorithm is a little more complicated because I'm going lane by lane. So it's a lot more details that I need. And what does Midas stand for? Midas was a king. Anything he touched turned to gold. You remember? Midas. What do you call it in Midas touch. So this is my Midas traffic control system. Okay, so Midas is back here, managing interacting demands and supplies. So what I've been talking about is basically supplies. Supplies are what the infrastructure is and the traffic signals. Demands are what the people are. Demands are the people using the infrastructure. So supplies are the network, the traffic signals, the RAM meters, the variable traffic signal. These are the supplies. Okay, I'm supplying the network to drivers, the humans, the society. Okay. So traffic supply management, these are operating this supply. Whereas demands in transportation are the people who are using it. The commuters are day-to-day travelers, trucks, emergency vehicles, pedestrians, they are the demand. Okay, so I want to do some demand management. The way I do the demand management, I load if I want to decrease the load, I'll put some pricing. So Yaf and Yin from Florida is looking at that problem. I'm going to put pricing on parking. I'm going to put pricing on using the road. So it's traffic demand management deals with controlling loads, time of day shifts, work staggering, travel advisories, pricing, incentive and all. There's a whole idea about incentive to make people behave differently. Okay, so if you use this route, I'll give you a $1 coupon to go buy coffee, maybe. So if you don't use this route, you won't get it. So that's an incentive. So the focus here is infrastructure and technology, and the focus here is behavior, travel behavior. I'm trying to answer your questions here. So I did this only. What I was doing, focusing was on this all along. But now I'm going to start focusing on both because they interact. Okay? It's like economics, supply and demand interact. Your point equilibrium, if they are stationary, if nothing changes, then after changing day to day and everything, you come to an equilibrium. That's your Nash equilibrium. Okay? And you work with that equilibrium. You decide on your traffic signals on that equilibrium. You decide on your roads on that equilibrium, and so on. If I change a road, the equilibrium changes. But we are hardly at an equilibrium. Look at yesterday we were traveling. It was not an equilibrium. Okay? There are accidents, there are incidents, there are weather, there are major events, they are fluctuating hardly. Equilibrium, in fact, is a fiction aspect, fictitious. Okay, we think there's an equilibrium. It's okay for planning, but for managing traffic, we need to think slightly differently. Okay, So let's talk about supply management. This is what I did before. I had some traffic engineers doing counts. They set something and forget it because they assume there's equilibrium in the network. So when you set the signals and forget it, it's equilibrium, it's working. But it works only very short time because something goes wrong. Recently, what is I'm going to start using these traffic sensors. I'm going to do a predictive engine, okay, which Rose had a little of it, but that was a weak point, but I'm going to make it stronger. And I'll do feedback control to proactively manage the traffic, okay? So prediction is key to proactive traffic management. A little later, and this is what I'm going to talk about, we haven't done it yet, it's an ongoing research project. So I'm going to come up with MIDAS, but I'm going to talk about bits and pieces of MIDAS. So there are some real-time algorithms. They're learning, they're learning the ratios, turn ratios, they're learning the travel times and everything. Because there's so much computing going on, I'm sending everything to the cloud to do the computation. So I don't have to worry too much about computation as long as I got the right data structures. And it's big data because I'm constantly getting data from the vehicles. Okay, so buzzwords, big data, learning, cloud computing, they're buzzwords. It's good to get the money. Okay, so the concept of operation is these cars, this is a highway, and these are ramp meters. These are traffic lights. The cars are going, and they're sending information to the cloud, okay? And they send information to the cloud. This is only artifact of stop. They really don't stop. They keep going. So every second, they're sending something to the cloud. So now here I've got lots of data here. So how am I going to analyze that data? Okay, that's the computational part. Okay, the objectives are, I'm explicitly considering the supply-demand interactions. I'm going to try to enhance mobility by decreasing travel times, increasing safety, and so on. I want to end up with stress, because there's another part of this which I'm not going to talk about, is to actually provide visualization to each driver. Okay, and I can also do this. I can have eco-driving, less emissions, less energy use. I can monitor that because do you know your cars, excepting for Volkswagen, actually gives you all that information. It has emission information. It has all that information. You can monitor that through the powertrain. Okay, so, but I don't want to increase infrastructure because it's expensive. Okay, I want to try to use what we have. So I want to keep the same infrastructure. And I want to think of MIDAS as a service system, servicing people, giving mobility service to traveler, to a manual car, to driverless car, to connected vehicle, to trucks, and so on. All those people who are requesting service. I'm going from here to here. MIDAS, give me a service. Okay, the Google would like to do this too. So, my competitor in this is Google. They got many more scientists, extremely bright scientists. Can I compete with them? Answer is only in some little places. Okay, so same thing. You saw this diagram before. I'm going to do a state estimation, data flow, decision systems. These are decisions now, not only on signals, but also on routing, driverless cars. It's on other, what should I put on the variable message signs? How should I advise drivers? Everything. So to advise drivers, I had to have a small behavioral component. If I say, do not use this road, I had to figure out what percentage will use it. Okay, so I have some behavioral components. Of course, as you build this up, you're going to get better and better behavioral components. Initially, they're very, very simple ones. Okay, certain percentage are going to use it. Market penetration. Okay, and the feedback and decision. Okay, back again to this diagram. Okay, now what's this proactive? Responsive one, Scoot and Scat are responsive. Something happens, they do some optimization, but the optimization is so slow. So, so the question is, how fast does it respond to change in traffic conditions? Does it respond to the current situation, and that's called reactive control, or does it respond to predicted situation? So that means you have to have another box looking at predictions. Okay? So give you a simple example. So suppose you want to follow this trajectory. You can think of time of day trajectory or something like that. What you can do open loop. Open loop is what they do now. Phoenix, Tucson, lots of cities just do open loop. Okay, at this time to use these controls, at this time to use these controls. So you notice there's a big difference between the actual traffic and what the open loop assumes. Okay, so we'll do responsive like Scoot and Scat. So it'll look at it and say, oh, you know what? I'm wrong. It should be here. I'm wrong. I should be here. So it sort of tries to follow, but there's a delay. So the red one is delayed to the green one. With proactive, what I do is I try to follow it. Back again, I'll never follow it exactly, because I can never predict what one driver is going to do, what not. But I can do a little better than assuming reactive control. So that's why I need my prediction. Okay, so general idea of it's again, I'm going to use the same examples, nothing different here. Okay, and I'm going to use a little different. Remember, this was my weak point. I'm going to try to change that. Okay, to make it more predictive, to be more proactive. Okay, so here proactive. So I'm using prediction and optimization to give me proactive traffic signal control. And I'm going to give you an animation of what I'm doing in terms of computation. Back again. So I want to let you know there's a prediction here, predictor here, predictor here. Okay, there's also inner loop, intersection, and okay, I went too fast. Intersection feedback control, and then we have regional feedback control. Now origins and destinations, which may be miles apart, maybe from your homes to your house. So those are miles apart. They give you load to the network flow control model. They give you timings to the intersection controller. Intersection control tells you, hey, you gave me these target timing. These are your actual timing. You ask that question. So there is some type of concurrency testing here to let them know that you are working with it. And then you give and then you put the act. So there's a little latency here, okay, when I send something. But the latency is a matter of quarter second, 1/10 of a second. Doesn't matter as far as traffic is concerned, because cars don't do too much in a quarter second. Okay, so there's a lot of work done. This is 2005 or something. Okay, there's lots of papers we wrote on roads, but now I'm going to add new sensors, and these are dashboard cameras. The cameras in the dashboard you can think my cell phone, okay? There's going to be some predictive analytics and demand management. So what is demand management? I'm going to give you pricing here, and I'm going to give you traveler information, which then will give me a different prediction, So these are now boxes which are doing both supply management and demand management. So, and to do all that, I need a lot of computation. So we are doing most of this computation in the cloud. Okay. So give you an example. This is city of Tempe. Okay. It is at a mesoscopic. It's not the biggest, because it's about 50 miles by 50 miles, Phoenix, if you look at all the origin and destination. This is only about 7 miles by 5 miles. So what you want to do, look at a medium level, this is at the network level. At the network level, you have maybe, say you're looking at this artery, there's traffic signal here, and so now you're looking at the microscopic level, where you got several signals in a row in this one. So you want to control the signals, which you want to provide to the mesoscopic level, which then you want to provide to the macroscopic level. Okay. So inside the box of Midas is, okay, that's very similar to Rhodes, control algorithm, very similar algorithm, but these are changed a bit. And to let you know, we did a PhD thesis in this area. Okay, how do you do real-time estimation of ratios very fast? And basically, generalized Kalman filtering and least square filtering and so on, some Bayesian stuff. Travel time analysis, discharge rates. Okay, those are master's thesis. Okay, so here's a animation. There's a traffic light here. There's a detector here. These are old-fashioned detectors. And there's a traffic light there. And I want to control this traffic light. So there's cars coming from here, cars coming from here, cars coming from here, cars coming from here. So they're coming from all those places. Okay? So here's only from the east. Okay? So the bunch of cars, they come in a platoon. Okay? And so when they go over here, I can start predicting when they're going to be there. Because now I know the travel time. Okay, I know the travel time. So when they go over the detectors, I have a good idea when they'll be there. So I got the predictions. Okay? And the predictions, I'm going to put them in a table. Okay? The table says that you notice is 0.3, because 30% of the probability this will turn right. Out of these 3 cars, there's 20% probability to turn left, 30% probability to turn right, because I'm getting this information online, real time. Okay, I'm updating that information. So next second, a car comes here. There's a red light, it stops here. Okay, so when it stops here, I know it's going to come later. Okay, and these cars are going to come earlier. So I'm filling this table up. Okay, I'm filling it up. Every second I'm filling it up. Okay. Now, if you notice, I put red here. Red means this is stop. I haven't decided on what schedule I'm going to put, so I'm going to put tentative schedule here, because I can change that. If there's an incident up there, why send the cars here? Okay. So I'm going to, maybe I'll change it. So I said tentatively schedule for demand management. So all at once, my predictions are cars that have already been there and cars that may come there. And that's going to be my decision how much time to give. Or when shall I turn that light green? So here's my phase order. These are phases. Okay. And this is what I showed you just now, these cars. If I give this phase at this time, these cars will be stopped. These cars may turn right, because in the US, we can turn right on red. Okay? So these cars can turn. These cars will be stopped. This is from the east. Guess what? I have the same thing from the west. I have the same thing from the south. I have the same thing from the north. I haven't put any numbers, but there are cars here. Okay, so now I have a big table there. I have to figure out how much green time to give here, and then how much green time to give here. And if I put green time here, these cars can go, these have to stop, these may go. If I put green time here, these cars can go, these cars have to stop. So notice what I'm doing. I'm coloring this table. Okay? So this says if I give green time like this, if it's only one case, okay, there are millions of possibilities, right? I can give this 1 second less and 1 second more and so on. So if you know of the knapsack problem, the knapsack problem is how much can I put in the knapsack? So I have a knapsack here. It's not a simple knapsack because there's an order here, but how much green time to put in the knapsack? And whenever I put a green time in the knapsack, I'm coloring this map. And when I color this, there's less delays here, more delays here. So with this map, for this, I can easily compute, simple Excel sheet will do, if I can easily compute the total delays and stuff from this diagram, right? But I want to try the millions of possibilities. Now this is your question. You asked me how many seconds? 52 seconds in here, or 53 or whatever it is. Every second is your resolution. And I'm using dynamic programming. So when I first did this, it just said, you're solving this. It's a small it's not a big problem on a computer. On a laptop, it can solve it in 1/10 of a second. Okay.
For how many lights and how many cars?
This is only one light. Only one intersection. Very good question. Only one intersection. Okay. So we can solve it from one intersection in matter of 1/10 of a second and so on. Now remember, I'm getting more and more powerful computers up in the cloud. Okay, so I can solve all of them. I can have each being solved separately in a distributed fashion. Now ROSE, I didn't tell you what ROSE stands for. Okay, ROSE stands for Real-Time Optimizing Distributed Effective System. We're doing distributed computing. So each intersection is sort of doing its own DP and sending information to the other intersection. So we're all sending information after solving the DP. So the might decide to choose the phase duration to maximize performance, and the performance is given by the traffic engineers. They say, I don't want stops, I want minimized pollution or whatever it is. Guess what? DP can do that easier. It's a simple computation for each of them. So now you know how Midas engine works. Hopefully I answered some of your question. It's data structure. So what we do is we move the pointer each time and solve whatever we have, whenever more data is there. So each time, every second, we move the pointer and solve for a rolling horizon for maybe 52 seconds in this case, because that was the difference between the two intersections. If the two intersections are closer, it's 30 seconds. Depending on how close the intersections are. So I showed you this before. You can, from these detectors, you can get traffic counts and approximate speeds, And these are called point detectors, Eulerian measurements. Okay. There are other point detectors. The new ones are, you can put a Bluetooth reader here, and if this car is carrying a Bluetooth, and a lot of modern cars have Bluetooth signatures, they send out some type of MAC address. You can get that MAC address. You'll get it here, and then you'll get it here. You can get travel times. So the Bluetooth signatures can give you travel times. You also have vehicle IDs. When you have toll collections, when you're sending out to collect tolls, you send out a signal from the vehicle, and that gives you you can take credit from whatever tolls you have. So there are other sensors, but now I'm going to talk about space-time sensors. So this GPS locator on this, because trucks have a GPS locator now. You can track each truck, and the truck will go along the way. Now, if you go into Washington State, Seattle website, they will tell you travel times. And they're based on these collection of these travel times on buses. Okay? And they call them travel probes, John. You can have remote sensors, which I talk, but we don't use them too much, okay, excepting in certain places. Because cell phones. And these are, you can use triangularization. So these are other sensors which are there. We don't have to spend money for them. They're already there, okay? So these are Lagrangian measurements because they give you travel times and trajectories. And remember I showed you those trajectories? And they're really important because now my sensors are giving me trajectories. They're not giving me the point detectors, okay? So we have now 3G, 4G telephone. We're getting fast information that provides streaming GPS data, gives accurate travel times and speeds, okay? There are engine sensors that monitor emissions. There's videos, so now I can use the videos on my camera. So you really don't need to talk on the phone. Just put the phone up there and start collecting data, okay? So here's an example. So what does this do? You have a camera and sees cars in front of you, and guess what? You're putting boxes in it. This is done real time. Real time, you're measuring where the cars are. You know where your car is. By image processing, you're getting where the lanes are. So now in front of each car that has this telephony, you're getting what's happening in front. Lots of data. Okay, you know where other cars are, where you know where your car is. Okay? So now I need to take all this real-time data, which now includes, you don't need the images, you only need the so we have a laptop in the car, which does that now, takes the data and does some real-time processing to say where the cars are. That's all I need, okay? And does some optimization in the traffic prediction. Okay, and actually, this was a PhD thesis by Zuyang Zhu, who did the title of it was last year, Data Fusion Approach to Real-Time Lane-Based Traffic Estimation. You're getting, from the trajectory data, you're finding out where the cars are, which lane has the cars, what's the density in each lane, what's the speed in each lane. Significant contribution to the state of the art. So, just to give you an idea of lane-based estimation, there's a lot of work. This is new to me, maybe for the last 10 years, but all the civil engineers have been working on traffic flow. They look at it as fluid flow through links. They think of fluid flow going through links, and they have some, they've got several works, pipes, newer. These are from 1960s to 1990s. They come up with a diagram that says, how does this fluid flow? But it's not a fluid flow. If you got self-driving vehicles, they're going to go in lanes. You got disconnected vehicles, they're going in lanes. They're not. So I'm changing this. You can do some simple stuff. You can have some characteristics of these links, how fast they go, and so on. You can have some heterogeneous. You can make some stochastic fluids in here, not necessarily simple fluids. You can do some things here, but as long as you keep it as a single lane, you're missing out a lot. So what I'm saying is, freeways are really lanes with lines in it. And these lines are not simple lines. You've got yellow lines, white lines, double yellow lines, and all that. So depending on the line, you have a permeability of the lines, okay? So you may have automated vehicles, which will have various lines. Only automated vehicles can go on that, or self-driving cars. You can have a connected vehicle. So really, we need models like this. We need models like this on freeways. We also need models like this on arterials, okay? So so now what I'm going to do is these cars are going to give me their ID and tell me where they are and what speed they are going on. And so now I got two types of measurements. I got these detectors, and I got measurements from the car, okay? So I'm getting trajectory vehicles, and so now I'm going to do data fusion of two sensors. Oh, actually, this is one type of sensor, but let's talk about three sensors. 1, 2, 3. Three sensors are sending out information. Okay. So data from a certain percentage of vehicles demanding. Now, this is your market penetration. How many cars are subscribing to Midas? Okay. And so it's a very simple thing. But we found out that if only 5% of the cars give information, you can predict better. But we can't control them as well because they're using their positions to predict traffic. So data fusion to predict demand of various supply services. Okay, so you got trucks, you got buses and all, they're asking some supply service. Okay, and the control scheme is really, again, approximate dynamic programming, because these dynamic programs are becoming larger and larger to try to point out. So you have to use some approximations. So we have done some approximate DP for that. And then you get a control selection, which actually in here and in here you can start changing demands. We're not quite done with the changing demands, but we're getting there. Yeah.
Have you used any other techniques for solving these type of constraints? So in formal methods still, there seems to be new developments around constraint solving. Maybe you've heard of satisfiability?
Constraint programming.
Yeah, and satisfiability modular theory. They seem to bring a breakthrough into this field.
I haven't. No.
I think they could be interesting, potentially.
Yeah.
I mean, Microsoft has been working on this for several years.
Yeah. So, but there's a certain difference here. It's dynamic. The D is important because you're always changing your demand. Every second it changes. So you're solving this, and because you have already solved the dynamic program already, it's much faster because you're changing these phases by a very little amount. Okay, so there is some.
It's kind of differential.
Yeah.
You're not solving it new.
Yeah. No, our initial condition is sort of from the last one.
Right.
So that's why we're able to solve it much faster.
So each time you solve a new problem.
Yeah, but we had to start off with the initial, and we change those. So we use the initial condition from the last cycle.
So what is the size of data we are talking about when you solve this DP parameters?
Well, it's the number of cars.
The number of car objects.
It's number of cars, and in 52 seconds, 3 lanes means, the number. So it's really a large integer, but not a gigantic integer. But if you take all of them together, then you need a lot more computing power. And so that's why we stopped thinking of it as being able to solve it on a single intersection, because roads were on a single intersection. But now we are solving it in the cloud, so we are really not worried about, as long as it's very efficient. And the way we are solving it, because our data structure is just a table. It's a circular table, depending on how many seconds you're going forward. 32 seconds will be a small circular table. 100 seconds will be a larger. And so we go down the line on that.
You have an order of the data, they can 2, 3, 5.
Sorry. Yeah. So what happens is when you start leading a big team, you don't know the details as much. I know the algorithmic details because I lead the algorithmic part. Yeah.
As you know, there exist some distributed control methods.
Yeah.
Yes.
Have I tried it here?
You have tried
No. Initially when I started looking at this problem years ago, I tried different approaches, linear programming, saturation control and all, and we said DP is the best way, and we haven't moved around from that. Unless some PhD student wants to come and try out different things. Yeah.
But you didn't test distributed methods, no? Distributed control methods.
Or it's distributed in the sense one intersection provides information at the second intersection. That's the way.
We have many sensing points.
Yeah.
And then in the control loop, we decide about the.
We can talk offline. I would challenge that is that much difference. You call it distributed control, but I'll tell you it's not that much difference. But we can talk offline. Okay, so here's, so we have these tables. You got these already on the way vehicles. These are tentatively scheduled vehicles, because certain, and all the computation is being done in the cloud to predict demand. I told you about this. And we are building this Midas control engine, but it's a little more complicated because we are trying to do lane level management, okay? So we have a PhD student looking at predicting at the lane level, okay? I had a PhD student who finished last year estimating at the lane level. Now I want to predict at the lane level. Why is that harder? Because you have to have a stochastic aspect. What's the probability that the car will change lanes? Okay, and there is a behavioral model that they'll change lane if there is a congestion over there. So the behavioral model is embedded in our predictive model. So this is what happens. So so you have to schedule this, and you have to schedule the traffic lights. So you're scheduling these and scheduling traffic lights, and you want to do them in real time. Okay. So we are also building something called MetroSim, because most of the traffic simulation models are at the link level. We want to build at the lane level. You would assume that traffic engineers would do this, right? But they only do it for small models. We want to do it for larger models. We want to be able to talk about lane level resolution for freeways and arterials. Okay. So there are lots of interesting research areas. So this is where I'm a shameless plug for PhD students to work in this area. Okay. So there's a lot of optimization and prediction algorithms that you can build. You can do, add dynamic programming. Maybe there are other ways to do this. Okay. How can we build decision making in these models? And the way we do it now, we are putting agents. Each vehicle is an agent which has its own memory and has its own objective. And we try to do something with that in trying to optimize. So we know these agents are doing that, but question, we don't know what agents are doing. It's an unobservable thing. So we need to do some calibration to figure out how many of these agents are trying to use the shortest route, how many of these agents are trying to use freeway routes, and so on. So it's a hard problem. And some of them will choose modes, some of them will choose routes, some of them will do both. They don't want to. I found out that people don't like to ride bicycles here, right? Right? We found out. Well, the thing is, it's a difficult mode to travel, so they don't want to use it. So the decisions of the agents in US is a little different decision of agents in Iran, on Germany, on Denmark. So we had to sort of put that in our model. And then, of course, how do people change? How do they take tolls? Tolls are, using money to travel, congestion pricing, tradable credits. So if you have some time, we can talk about tradable credits in smart cities. And so tradable credits are becoming a way to try to control populations. So you give credits to people who are choosing better routes and let them trade it if they're, the people who want to use it. So there's something saying that you can make a city more sustainable with tradable credits. Yeah.
Regarding social and cultural influences, are there people who have worked out quantitative models that quantify these influences?
There are people who are working on tradable credits.
No, I mean the previous one, driver decision making.
Oh, yeah.
So I can imagine, depending on the behavior of the driver in different cultures, you need to tune your model differently.
Yeah, so this is one of my pet peeves. All the people who do demand modeling and so on hardly ever look at, they don't want to, it's politically incorrect to that. It's not for me. Okay, New York drivers are worse drivers than Arizona driver. So I want to be able to put that in my model. Okay, but they don't want to do that. The way I do it in the model is I learn how their behavior is, because you can learn their behavior from the tracking of their cars.
How about those people who do cultural studies and social sciences? Is there any way to interface those outputs to this research, or do you think it's proper?
No, there are people who look at how drivers drive, but they don't interface with traffic control systems. They're different.
Is there a prospect of connecting this?
I don't know. You're asking me. I can only do so many things, right? So here's something which interesting. This result, this was just published. So let's look at the decision making at this level, and you can think of, I want to provide signals. I want to provide signals here, and I also want to provide routes. So I'm doing two things now, and this is to do with routes for self-driving vehicles. Okay, so providing routes means I'm doing demand management. Providing signals, I'm doing supply management. I want to do that together. Okay, so I want to set signals and provide routes. And of course, if I provide routes on one lane, I'll need a lot of signals. So there is some type of balancing I have to do here. So here's my lane level map here. So these, you can think of, these are origins and destination. The blues are origin and destination, and these are signals in here. And the signal, for example, here says this is a right turner, this is a left turner, this is a straight through. So signals are in here. Okay, it's a lane level. There are only very simple lanes here. There's one lane here, one lane there. This lane can go this way or this way. I can put more lanes in this, but it gets more complicated. So I call this a space. Me and my co-authors called it space, phase, time hypernetwork. Okay, so I'm going to try to explain that. Is right now you can think of this network only as a space network. It's just only space, right? There's no time involved here. But when I put the phases, all at once I'm putting time. Okay, by the way, this appeared in this Transportation Research Part B last year. Once I'm putting phase, so this is, for example, this red one goes through here, may stop here if the phase is red. If the phase is green, I'll go over here. May stop here, I'll go over here. So you notice that that's the red one. The blue one is over here, okay? If they both come here at the same time, there's conflict here. I have to either give it to the red or I have to give it to the blue. So I have to make the decision there, okay? So I'm going to do this concurrently. And again, I'm not going to give you all the details. We can, now with Midas, we can provide guidance to each car, okay? And I'm going to have two things. They're called vehicle guidance subproblem and traffic signal optimization subproblem. Now they are treated like exogenous constraint to each other. So it's a bi-level problem, okay? There's one level is signal timing, the second level is route vehicle guidance, okay? So I can do this together because now Midas algorithm is up in the cloud, is getting all that information. And I can give route guidance, I can give traffic signals at the same time, okay? So vehicles are going on time-dependent shortest paths. Okay, they are not regular shortest, but time-dependent because now time comes in. And individual signals, their phases are at different times. At this time, it's red phases. So the network changes depending on the phases. So that's why we got phase timing, shortest route travel time, which is space-time diagrams. So how do you solve that? Well, what we do is we relax these constraints because it's quite hard, and we solve it approximately with using we get pseudo polynomial algorithms for this, okay? we had to do two things. First of all, we had to expand the networks to introduce intersection and time. So here's a regular network. This is an old-fashioned network. This is a node link. Now it is a node which is got phases in it. So it's got phases in this and got origins and destination in it. And now these are my trajectories. Okay, the trajectory, this is the one trajectory. It stops here because of this is another trajectory. And you got, for each vehicle, you got all these trajectories. So what I want to do is I want to optimize these trajectories so I minimize either the stops or the delays or whatever you tell me to do. Okay, so it can be done. And here's a larger view which says, I will take this, I showed you that they all compete for this. So I'll do phase scheduling and demand scheduling at the same time. Okay, phase scheduling means I'm going to set signals, and demand scheduling, I'm going to give routes. Okay, I think this is the last slide on this, and I'm going to end my talk soon after the last slides. Okay, so what does MIDAS CPS? First of all, do you agree it's a CPS? Do you agree? Okay, we can go back to the first diagram, okay? It's got transportation as a domain. It does all sorts of computing, and it's a control system. It's a human in the loop control system. It's got human factors. It got humans in the loop, and we are trying to have a service system for the humans. It proactively responds by monitoring traffic, learning what's happening, travel times, ratios, predicting what's going to happen in the next 50 seconds or whatever it is, and responding to it. Okay. Some fundamental contributions. So we did this real time. So my colleague, Boshan Lee, is publishing papers in how do you do this moving images in real time. My students are doing this lane-based traffic flow theory, which has not been done before. We are using Lagrangian sensors. That means we are using cell phones, and it doesn't cost more. Everyone has a cell phone, okay? Not everyone. 90% of the people have cell phones. How many of you do not have a smartphone? You don't have a smartphone, so you won't be in this experiment, but everyone else will be, right? And lane-based optimal control, which is traffic signals are lane-based, RAM metering is lane-based. Now speed controls on the freeways are lane-based. Lane changing is lane-based and everything. So again, I'm putting the same future vision, excepting now I'm saying that we're going to be using 3G, 4G, 5G, 6G, whatever it is. Okay? And we're going to provide appropriate service by scheduling green phases, or also doing other things too. We're going to provide supplies, message sign, vehicle advisories, congestion pricing in the vehicle itself, which will tell you how much will it cost to go on this road, okay? Or how much incentive you'll get if you don't go on this road, which is a better way of looking at it. So now we're going to say, in the far future, a little more later future, we can, now I'm going to talk about the privacy issue, and you can decide whether you want to use the service or not. Right now, we decide whether you want to use Google service. It's free, okay? You can decide you want to use MIDAS service or not. What does the MIDAS service do? It provides a little more options for you as a driver to go through the system better, okay? That's it. Thank you very much.
We have ample time for questions. Let's take several questions.
Yes. You mentioned that you included driver behavior in your model to predict better, right? Because drivers behave differently in different places.
Yeah.
And you learn that from how they drive.
Yeah, only driving behavior.
Driving.
And there's also another behavior which we haven't quite done because we're doing offline. How do they take prizes? Whether you're willing to take a prize to travel or whether you're willing to take an incentive. There's a colleague of mine who's doing work in that area right now. Mhm.
you adapt your system, change your system?
That's the first one. Rose does that. So we noticed during the time, because we tried it out near the university, during the time the university students were coming there, they were going much faster. At night, when it's leisurely, people are driving much slower there. And also we noticed, because in Tucson, where I was, certain areas you get old retired people, and the university you don't get retired people, they're students, and they are much more aggressive drivers. So we noticed that. So that doesn't matter anymore now, because I figure out the discharge rate. That's the proxy measure on how aggressively they drive. Okay.
So how fast this feedback loop is supposed to be to adapt your system?
Okay. Also very good question. So the green time is only for a short time when people are leaving the green time, and then next time you see, so every cycle, although we don't have a cycle thing, but next time you have the same phase, you have updated it. Because if you have residual Qs, because you got Q measurements or Q estimation. If you got residual Qs, that means you didn't estimate your discharge rate well enough, and you keep having residual Qs. I have some papers on that. If you keep having your residual Qs, that means your service time is wrong. So basically, we update our service times in these Qs. Okay. So idea is to try to go to zero residual Q after each cycle.
So I have more questions, but I prefer to take questions from the audience. Yes.
I don't have any problem with CPS name, okay. But I think it's a large scale control system, because you solve computation concern with cloud computing, and you solve actually communication concern with fiber optic and etc.
Yeah.
And I think I'm looking for, I think you didn't consider any model for computation to redesign, for example, control for control. I'm thinking, where is the CPS? It's a large scale control system.
Mm-hmm.
So if I may rephrase the question, how CPS is different from control, right? How your system is different from traditional control?
Okay, so he will say this is not traditional control. Sorry, I'm putting words in your mouth. This is more than it's not traditional. It's an integration. So the focus on integration here. You're integrating a whole bunch of different engineering disciplines, and with a common goal of trying to improve service for transportation. So the focus is more on integration rather than, and we tried, all these little bits and pieces we investigated before putting it in the system. We investigated whether we should cycle time or whether we use phases, then decided phases. We investigated whether we should use dynamic programming. What interval should you use? Every second, every half a second, every 2 seconds? And we realized 1 second is enough. We tried various levels of discretization. We tried some other approaches on control. So because I had 3 or 4 people working, let's try this control type of method. Let's try optimization method, not control. And so through this mechanism, we were able to come up with some contributions. But the goal was integration.
I think that there is this one more point, that in traditional control you do not consider the execution time or the computation time of the control decision making. Do you?
Not necessarily. In many cases, you consider this time. When you are discretizing a system anywhere, the sampling curiosity is all you consider when you are dealing with a discrete system or in general digital systems. That's been the basic idea since its beginning. So I think that the point is that somehow the issue of the cyber side has not been highlighted. I believe
Maybe you're right. Maybe you're right. But I would ask you what you mean by cyber.
it's a big issue. Anyway,
So one more.
somehow a network
Yeah.
shall be considered, and the effects of the network on the problem should be highlighted in a way. I mean, to consider what we might have.
Effect of which network?
I mean, there's the communication network.
Communication network. Okay.
Yes. Then you might have packet dropout. You might have missing packet. You might have router overflowing. Whatever the typical problems which may arise in network control system
Yeah.
in general.
Yeah.
So when we say cyber physical, one may expect that these points are also highlighted and discussed.
Yeah.
I personally have another question, just a brief explanation.
No, I agree. So here's a hierarchy called at what application level you're going to work on. You know, we could have had some people on our team, but we didn't have enough money to look at issues on network flow.
Control systems, anyway, I mean, the
Yeah.
name that is given to this topic.
So we have transportation network. We're controlling transportation networks. Okay. Another thing I want to point out to control theorists is you know, my master's is in control theory, and over there we looked at. It's from aeronautics and astronautics. So we looked at guiding rocket ships to the moon. And so what the data we're getting is we're getting data, quantized data, every few, maybe a minute later, you know, delayed. And so what our controls is sending a thrust here, thrust there, so on. So there's already a delay there. And the models we used is control systems, okay? So your control system at a more micro level, I think. Our control systems were Kalman filtering to predict. Optimal control to decide where to put the thrust and how much thrust to put, okay? So all the little things, what model did we use for a third order system, okay? So now you'll say, you know, where's the control system here? The whole thing is a control system at a higher resolution. We're not looking at the lowest resolution, and I don't think aeronautics and astronautics people do that right now. Maybe only within the plane they do it, but not sending rocket ship to the moon. So, sorry.
You mentioned that you have considered cyber security
Okay.
point of view. Can you have some more?
Okay, so see, I'm not a cybersecurity guy. Zhizhang Huang is, okay.
Just a brief.
So the idea is,
Or what are the issues you are considering right now?
yeah, idea is the issues whether we can hack in, okay, not hack in for privacy, hack in for disruption,
Yes, of course.
and he's looking at the issues of how do you do that. So there's encryption. So only encryption here is that someone cannot figure out how to change the traffic lights without from external.
Known protocols for data encryption, obviously that can be very simple.
He's using the idea is that I'm giving you you know, again I'm out of my realm here because you know I can only do so many things, right? So he says what he's doing is he's sending a key, and a key which every few seconds or every minute changing keys, change down to the traffic signal. So only person who can break the key is the one who sent it. So the external person, as soon as he breaks it, there's another key there. So he has to really break it fast within a few seconds to be able to do that. Is that a good system?
That's enough.
So we still have time for more questions. Yes?
When there is a heavy congestion in the traffic, how do you make sure that your algorithm is working in a better manner and it's not the inherent of the problem?
Okay, yeah, good point. So skipped a lot of details on this. So what happens is there's something called saturation, congestion saturation. So what, you know, and it's like a queuing model. Up to a point, it's easy. And then it starts going up. And you can, or what Rhodes does and Midas does is moves it a little. But after that, you can't do anything. There are too many cars for the road. And it doesn't matter whether you have, the only way this is to design an overpass or something like that. You just can't handle it. What the Japanese have done to do that is they just don't send cars down the road. Okay, they gate it 5 miles up. If you're going into Osaka, you should go early morning or certain late times. Because if you want to go at 8 o'clock, you can't get into the roads. You have to go way off. So that's the type of thing you do. You demand manage through gating. Gating means you stop cars going in. We don't do that in US, but we will do that eventually.
I think we can take one more question before we go for lunch.
Just two questions.
Okay, we'll see how long it takes. Go ahead.
It's a good point to solve the problem locally for each intersection. It makes the approach scalable and which is necessary for this type of problem. What assures the global good behavior and the whole city traffic is managed properly with just local sites?
Okay, so this is an academic question. What's the optimal behavior of a stochastic process where you're learning the stochastic aspects of it? You can always get all the data and say what would have been the best if you have every data, every person and everything. Or you can say without knowledge, what's the best? So we can only do through simulation, how well we are doing compared to any other system. But is that global optimum? Global optimum is only if there was someone who tells you in future what the cars are, and we don't have that someone. Because someone tells me in the future that that's going to be the demand, this is going to be the exact, because remember, demand is stochastic, behavior is stochastic, and no one is going to tell me what's exact going to be. So the idea of having the global optimum is another fictitious thing. There is no such thing. All we can do is, given your scenario, how well we do with the scenario. And with that, we can do is only evaluate through simulations.
It seems that, for example, we manage each intersections by a police officer locally. But when we have a global view of the whole city, we can make a better decision.
Yeah.
I didn't saw in Midas that you...
Oh, we had done that. With Rose, we had done that. So through simulation, we don't simulate only one intersection. We simulate, in the simulation that I showed, there were 12 intersections or something that we simulated, and we did well. Okay, so we don't simulate. And simulation also takes a lot of time. Okay,
But the
so,
optimization problem is also global, right? So you're solving
Yeah.
the whole
Yeah.
set of equations. It's not just one intersection, it's just like
but again, we're trying to solve something that's stochastic, and we only solve it for that scenario that keeps coming, okay? And the way to evaluate any type of system like that is to me, for complicated system, is through simulation.
Okay, I know there are more questions, but we are approaching lunchtime. So I suggest we take the rest of the questions during lunch. So let's give people a big round of applause.
Thank you.